Good evening to Ananda. Good evening. So please kindly confirm audio video on screen once. Good evening to Ananda. Please kindly confirm audio video on screen. So okay, we will wait for 2 or 3 minutes. So after that, we will be continuing with yesterday class, steady state stability analysis. Yeah. So next, we'll be continuing with this today. Actually, in case of alternator, we have two types of alternators actually. One we will say a round rotor alternator, other one is a salient pole machine, right? So I'll write here. Two types of alternators are there. Types of alternators exist generally. One, the cylindrical rotor type. Cylindrical rotor type. Second one will be salient pole rotor type. Salient pole rotor type. So salient pole rotor in the sense, we get the rotor of the synchronous machine, something like this. So round rotor in the sense we have a circular solid body, right? As a round rotor, or you can say cylindrical rotor machine, right? Next. Look here. Say I want to take up the power equations, real power equation of the cylindrical rotor machine, as well as for salient pole machine, how is a real power equation. These two things I am going to consider. Okay, particularly in case of cylindrical rotor type machine, electrical power equation would be mod E into mod V by XD into sine delta. Okay, delta is a rotor angular difference between synchronous generator and the infinite bus. Rotor angular difference between synchronous generator and infinite bus. Yeah, fine. And in case of salient pole machine, we have two reactances. One is a direct axis reactance. Next one is a quadrature axis reactance. Right? So in case of salient pole machine, we have two axes, quadrature axis and direct axis. And direct axis reactance will be generally greater compared to quadrature axis reactance in case of salient pole machine. Whereas in cylindrical rotor machine, the direct axis and quadrature axis reactances will be equal. The direct axis and quadrature axis reactances will be equal in case of the cylindrical rotor type. Okay, now let me give you expression for real power in case of salient pole synchronous generator. Expression for the real power in case of salient pole generator. It's very simple. Mod E into mod V by XD into sine delta, okay, plus 1 by xq minus 1 by xd. Just follow it. I'm not doing any derivation. This derivation you might be studying in synchronous machines. Just I am taking that equation multiplied with mod v square by 2 into sine 2 delta. Like this, we are going to get expression for the electrical power in case of the what we call salient pole machine. For example, if you draw power angle curve, one more thing, I am assuming both alternators as lossless here. Both alternators we are assuming as lossless. Okay, listen kindly. If you draw the power angle curve for the cylindrical rotor type, we get only sine delta. So it will be simple sinusoidal signal we have. Let me show it. Just have a look here. First, cylindrical rotor machine we are taking up. Cylindrical rotor machine power angle curve. So on the x-axis we are showing delta. On the x-axis we are showing delta. On the y-axis we are showing the real power. It is simple sinusoidal signal. So power variation with respect to delta comes something like this. Okay, this is the value of E into V by XD. This is the value EV by XD. That's what we have shown here, EV by XD. And that we are going to call sometimes as maximum power transfer capacity of the network. Maximum power transfer capacity of the network. Okay? Yeah, next. And at what angle we are going to get this one? At an angle of 90 degrees. We are going to get this at an angle of 90 degrees. So this is for power angle curve, means P delta curve for cylindrical rotor machine. Yeah, let's draw that power angle curve for salient pole machine also. Thereby we are going to decide. We are going to decide where we are going to get P maximum for that. Then we are going to make some simple comparisons between them. That's it. Okay. Yeah. So let's show again x and y axis. On the x axis we are showing delta. On the y axis we are going to show power. Observe here. This is electrical power and this is delta. Simple. Listen here. Simple. Look here. It is one signal sine delta. EV by XD into sine delta. This we are going to call generally electromagnetic power. First term what we have here is going to be called as electromagnetic power. And the remaining term what we have, 1 by xq minus 1 by xd into mod v square by 2 into sine 2 delta. This term we are going to name it as reluctance power. Okay, now you see, first of all, this electromagnetic power, it is a function of sine delta, means it's a sinusoidal signal. And reluctance power is function of sine 2 delta, right? Reluctance power is a function of sine 2 delta, means you get sine 2 delta signal. Then we have to add these two signals together. One signal is sine delta signal, other signal is sine 2 delta. Then we are going to get the resultant electrical power with respect to delta. Very simple. So in the next slide, I will show first Sine delta signal, maybe like this I'm going to show, is EV by XT into sine delta signal. EV by XT into sine delta signal, or you say it is electromagnetic power. Electromagnetic power. Next, we have reluctance power, right? Reluctance power is sine 2 delta signal. Let me show that. Sine 2 delta signal, it may come like this now. Sine 2 delta signal like this. But magnitude of the reluctance power is very, very less compared to electromagnetic power. Magnitude of the reluctance power is very, very less compared to the electromagnetic power. So that the sine 2 delta signal height comes to be very, very small. Now, we have to add, this is reluctance. P reluctance. Now we have to add that electromagnetic power sine signal and this reluctance power sine delta signal together. If you add these two, we are going to get the resulting signal, maybe something like this. Like this, we can expect a signal of the power with respect to delta after adding both electromagnetic power as well as the reluctance power. Now, very, very simple thing I am asking. Very, very simple. See, this is a point at which we are getting the maximum power. This is a point at which we are getting the maximum power. And at what angle we are getting that one? At what angle we are going to get that? Let me show you a different color, the dots. At what angle we are going to get that? See, definitely this P maximum is going to come in case of salient pole machine, definitely at an angle less than 90 degree. Less than 90 degree, may not be 45 degree. Manikanta Kumar, it's not 45 degree. It will be less than 90 degree, but definitely more than 45 degree. Definitely more than 45 degrees, right? So this is power angle curve for salient pole machine. Salient pole machine. Power angle curve for salient pole machine. Now, whatever I discussed till now, that I am going to write. Just observe here. In round rotor machine, round rotor, nothing but cylindrical. Round rotor machine, P max occurs at what angle? Delta equals to 90 degrees. Whereas in salient pole rotor machine, P max occurs at how much angle? Delta less than 90 degrees. We are going to get the P maximum delta less than 90 degrees. Okay. Right. Next, for small comment I want to make here. Just all of you, just concentrate here what I am saying. Concentrate here. When we can say system is stable? When in case of steady state only we are talking now. Only we are talking about steady state. In case of steady state, when we can say the system is stable? Tell me please. Whenever we are standing at a point where if d delta by dt is, dp by d delta is positive, dp by d delta is positive, at that point we can say the system is stable. Means if we are standing on the positive slope point, we can say the system is stable under steady state operation. Clear? Next, listen please. You compare these two slopes here, in this region, the system will be stable. In this region, the system will be stable. Whereas in this region, the system will be unstable. Yes or no? In this region, the system will be unstable. In the similar way here also, I am showing. In this region, the system will be stable. Positive slope region, the system will be stable. Whereas in the negative slope region where we have shown here, in this region, the system will be unstable. See, at very low angle, listen all of you, listen kindly. At some angle, I will say 30 degree, low angle, or else 20 degree angle, 30 degree angle, or you can say 20 degree angle. At lower angles, which machine will have more stability? Which machine will have more stability? Is it salient pole machine or cylindrical rotor machine? At low angles, maybe 30 degree point, which machine will have more stability? Salient pole. Why? The simple reason is the slope of this curve looks to be definitely large compared to slope of this curve at 30-degree angles. So at operating angles of the system, salient pole machine will be more stable as compared to the cylindrical rotor machine. In which state of operation I am saying that? In which state of operation I am saying that? Only steady state operation will we are talking about. Okay. So I'll say in the next slide. For lower operating angles, right? If in brackets you want delta less than 45 degrees, something delta less than 45 degrees. Salient pole machine will be more stable compared to cylindrical rotor machine, round rotor machine under steady state. Understood. I think all of you getting this point. Simple. But there is one more term we have as a transient stability, right? We have one more term like transient stability. Particularly in case of transient stability, there is one more factor which is going to show great effect on the system stability, that is weight of the rotor. Or else we can call in technical terminology moment of inertia of the rotor. That is one of the factors definitely which is deciding the system stability, particularly in the transient time. For example, if you compare the moment of inertia, please listen here. If you say moment of inertia, which machine will have more moment of inertia here? Is it cylindrical or salient pole? You feel simply weight the volume of rotor, you can think simply. Which machine will have more volume generally for a given rating? Definitely cylindrical one. So cylindrical rotor machine will be having higher moment of inertia, so that this machine will have more transient stability compared to salient pole type. Okay, yeah. So I'm writing that statement also. I will explain transient stability later. In view of transient stability, round rotor machine will be more stable, compared to salient pole machine, because round rotor machine will have high moment of inertia. Right? Round rotor machine will have high moment of inertia. Right. So I think all of you getting this point. Next. Next, I'm taking up next one here. Next one, that is alternator connected to infinite bus bar. Through a long transmission line wire. Okay, yeah. I'm taking up next heading. Alternator connected to infinite bus to a long transmission line. Alternator connected to infinite bus through a long transmission line. Yeah, see, simple, Sai Charan. If the moment of inertia of the rotor body is more, moment of inertia of the rotor body is more, it won't accept the speed changes suddenly. It won't accept speed changes suddenly. It won't decrease the speed suddenly as well as it won't increase the speed suddenly. That property makes the speed close to synchronous speed only. By that way, change in the angle because of disturbance expected will be less. Okay? Yeah. Next one. Look here, look here. So this is one alternator I am showing. Alternator. And this is one long transmission line wire. And this is connected to infinite bus. Infinite bus. And this long transmission line will have some ABCD parameters. ABCD parameters of long transmission line. This you will study in TND. This you will study in TND later. Right? Right? Long transmission line, ABCD parameters. And this is our generator. This is our power generator. Actually, this power generator will have some internal reactors. Yes or no? As we are doing steady state operation here, we have to take steady state reactance for this machine definitely. Okay. Let me draw per phase network of this. Let me draw the per phase network of this. For example, if we take generator, the generator we are going to draw as a voltage source in series with the internal impedance JXT, steady state operation. And then at the end of this generator, we have that ABCD model, so-called transmission line network. Just follow the things what I have seen. This is a transmission line network ABCD, AL, BL, CL, DL, and infinite bus. How we model infinite bus in the equivalent circuit? How we will model the infinite bus in the equivalent circuit? We say it is simply an AC voltage source with zero internal impedance. Right? AC voltage source with zero internal impedance. Yeah. Next one. Look here. This infinite bus voltage I am choosing as the reference, mod B at angle 0 degree. This internal voltage of generator we are choosing as mod E at angle delta. Internal voltage of generator we are choosing as mod E at angle delta, and the infinite bus voltage we are choosing as mod B at angle 0 degree. Next. See, this whole network what we have means this JXD and ABCD of line. JXD and this ABCD of line, that we are going to transform into a single ABCD model. Means maybe in network analysis you might have studied that simply if two networks are connected in cascade, take up the resultant ABCD as multiplication of two ABCD matrices. By some technique, whatever it is, forget about it now. I am going to take up the whole ABCD, including the JXT. So I will redraw this network. This is the AC voltage source of generator, and the whole network between the two AC voltage sources was represented in the manner of ABCD parameters, equivalent ABCD parameters, and this is the infinite bus voltage source. Infinite bus voltage source. This is mod E angle delta. So if you want to write for your clarity, this is equivalent ABCD network between the two voltage sources. Okay, next thing. Please draw these things quickly. That we will move to general notation of ABCD. I will tell you. General, how we are going to represent this A in the standard notation, B, C, D. These things I will tell. Yeah. So I'm taking up the next slide, let us say. Next slide. In general, parameter A we are going to call as mod A at angle alpha. Parameter B we write it as mod B at angle beta. Parameter C we are going to call as mod C at angle gamma. And whereas parameter D is mod D at angle delta. Like this, we are going to write the ABCD parameters. Mod A at angle alpha, mod B at angle beta, mod C at angle gamma, mod D at angle delta. Like this, we are going to write the ABCD in the standard notation. Now, see, What is the expression for? What is the expression for real power injected into the infinite bus? What is the expression for the real power injected into the infinite bus? That is our interest. Anyhow, I'm not going with any derivation right now. I'm not going with any derivation right now. I will give you directly this equation in terms of ABCD parameters. That you try to remember. That you try to remember. If time comes, I will discuss about the derivation. Okay? Yeah. Okay. Electrical power. Electrical power injected into infinite bus. Injected into infinite bus. Okay? PE. Just follow this. Mod E into mod B by mod B cos theta minus delta minus mod A by mod B mod B square cos theta minus alpha. Just go through the equation clearly. Mod E, mod B are voltage sources at two sides. Parameter B, look here. Look the name of parameter B now. Look this parameter B name. This parameter B is going to be called as short circuit transfer impedance. Its name is short circuit transfer impedance. Short circuit transfer impedance. Okay, just it's a network theory term, what I said. Network theory term, that's the definition of B. Name of parameter B. Don't think deep about it. You can ask me again, what is that short circuits are, what is the transfer impedance? Okay, not needed right now, not needed right now. It is simply short circuit transfer impedance. That name you have to remember. Okay, next, come back to this. See, this power equation if you observe, it is coming in terms of parameters A and B only, right? Parameters A and B. Parameter A, you know, mod A at angle alpha. This is an angle of A alpha. And this is parameter B angle beta, mod A, mod B, mod B. That's it. What is delta we said? That is the angular difference between the two voltage sources. Angular difference between the two voltage sources. Okay, next. Listen. Making some assumptions now. Making some assumptions. This mod E, mod B, right? As well as parameters A and B are constants. Next. A, comma B, comma mod E, comma mod B are constants. Which are variables now here? After making all these things as constants, which are variables? Which is variable? Delta. Yes or no? Only one variable here is obviously delta. Delta. That's what we have done earlier also. We have drawn power variation with respect to delta. Power angle curve, in the sense power variation with respect to delta. Here also, we are going to concentrate to think about the power variation with respect to delta 1. With respect to delta. Now, with respect to the delta, what is the condition for maximum power transfer? With respect to the delta, what is the condition for the maximum power transfer? See, it's a non-linear shape, right? Cosine of beta minus delta we have, it's a non-linear one. If it's a non-linear variation, what is the condition to get maximum? What is the condition to get maximum? We have to take the first differential value that we should make it equals to 0 to obtain the condition for maximum. Yeah, all of you getting this one? Please tell me. Okay, I will write in the next slide. Condition to obtain PE max, maximum real power injected into the infinite bus. Maximum real power injected into the infinite bus. That is dPE by d delta is equals to 0. What is dPE by d delta? Just differentiate that real power with respect to delta. Get this one. Differentiate this real power with respect to delta. What do you get now? Mod E by mod B. Mod E into mod B by mod B. Cos differentiation will be, you can say minus sign of beta minus delta. Again, beta minus delta was differentiated with respect to delta, you get minus 1. So minus will be cancelled. So you can get here mod E, mod B by mod B sine beta minus delta. And if you differentiate that next term, it is completely free from delta, right? Completely free from delta. So second term will be 0. Now, as we are saying, dp by dpe by d delta is equal to 0. That implies mod e into mod v by parameter b magnitude into sine beta minus delta value is equals to 0. Has already assumed that the voltage magnitudes are constant. If you want, you can consider partial derivative also without making the remaining numbers as constants. Okay. As I have assumed that remaining values are constants, I am going with directly differentiation here. If you want, you can write partial derivative also, Vishnu. There is no issue with that. Yeah, let's move. See, as this is constant, it won't become 0. So if you can send this to the other side, so I can say simply sine of beta minus delta value shall become 0. What do you mean by sine beta minus delta 0? Beta minus delta value will be equals to 0. Beta minus delta equals to 0 degree. What is that condition we have to get now? Delta is equals to beta is a condition. Delta is equals to beta is a condition. Okay? Delta equals to beta is a condition. Means at what power angle or at what load angle we are going to get the maximum power transfer. Means that is the delta equals to beta. See, this delta what we have studied earlier, we said that as a rotor angular difference, one word, else you can call that as power angle, because that is the angle which is going to decide mainly the real power flow, or else you can call this as torque angle also. You can call the same thing as a torque angle also. All these three words will be same. Torque angle, power angle, or you can say load angle. This can also be called as load angle, because this is the angle on which mainly the real power flow is going to be decided. All these names will be same in the power system analysis. Okay. Now, delta equals to beta is a condition for the P maximum. And simply you substitute the delta equals to beta into the real power equation so that we are going to get the maximum power. Yeah, let's move in the next slide. Value of P max, maximum real power. That is nothing but the value of P at an angle delta is equals to beta. Kindly observe. So simply in this one, if you keep beta in place of delta, so cos of beta means beta you get cos 0, 1. So first term will be EV by mod B minus mod A by mod B square, cos beta means R. That's it. So I can say this as mod E into mod B by mod B cos 0, 1 minus mod A by mod B square cosine beta minus alpha. This is PE maximum. Rosemary, we are discussing this only for cylindrical rotor machine. We are discussing this one only for the cylindrical rotor machine. Not for sailing. Okay, next. See, what is this another name you can say? What is the another name for this one? Anybody tell me? What's the another name for this one? P maximum, or what's the another name? Steady state power limit, or you can say steady state stability limit. This can also be called as steady state stability limit. Steady state power transmission capacity. Steady state power transfer capacity of the network. Steady state maximum power transfer capacity of the network. Maximum power transfer capacity of network. Yeah, somebody asked me, sir, why we are discussing about this? What is the need of this one? I think you come to know what is the need of this. Because we can't say all the time generator directly connected to the grid. Means we can't say always generator is directly connected to the infinite bus bar. Generator may be connected to infinite bus bar through a transmission line wire and transformer and all, right? In that situation, to calculate the maximum power transfer capacity of network, it is not sufficient to take only generator reactance. It's not sufficient to take the only generator reactance. We should involve whole network, whatever you have between the generator and the infinite bus in the analysis. Okay. So in general, any network we have doesn't matter. Between generator and infinite bus, maximum power transfer capacity equation will be like this. So simply, whatever the network we have, yeah, between the generator and infinite bus, that we should convert into ABCD model, and we should pick up the parameters A and B to calculate the PE maximum as well as the real power flow calculations. Okay, fine. Next. I'm going to make some sort of simplifications now. One simplification is the network what you have considered here in this network, shunt element is neglected. Generally, we have for practical transmission line, we have natural shunt capacitance effect, right? Natural shunt capacitance effect, right? We have some natural shunt capacitance effect that we are going to neglect. See, if you neglect that shunt element in the network, what elements we have now? We have series resistance and series reactance. That's it. Is the whole network what we have between generator and infinite bus will be acting as series impedance R plus JX form. Okay, that I'm going to take. Yeah. So I'll say by neglecting shunt elements in the network. By neglecting shunt elements in the network. Observe it. By neglecting the shunt elements, I can say this is a generator and this is Rx. This is your infinite bus. Okay. Yeah. Next. See, this generator voltage I am showing mod at angle delta. Yeah, don't bother about internal reactance of generator here. Internal reactance of generator was taken into this network only. Okay, I'm not writing separately XD. That XD was taken into this reactance already. So this is R plus JX form, and the infinite bus voltage is mod V at 90. And this R plus JX is a series impedance of the network. R plus JX is series impedance of the network. Okay. So that Z is equals to, we'll say R plus JX, and this you can write something like mod Z at an angle of theta in polar form. In polar form, you can write it as mod Z at an angle theta. What is the value of mod Z here? Root of R square plus X square. That's the mod Z. And what is theta? Tan inverse of X by R ratio. Tan inverse of X by R ratio. Mod Z. Assume all these delta like neglecting shunt elements and transmission line, correct mathematical expression. It may not be, Gopiraju, it may not be. The practical maximum power transfer capacity of network means this one only. Practical maximum power transfer capacity of the network means this one only without neglecting the shunt elements, right? We should consider it. But even though you consider the shunt elements, we may not have a great effect. That's the thing what I was interested to tell you. Why it is so means, listen here, Gopiraju, listen here. Generally, whatever the parameter B we have taken here, that is generally representing series impedance of network. Even though you consider the shunt element or neglect the shunt element, it may not show, I'm saying you again, it may not show a great effect on the maximum power transfer value. That's why we are neglecting the shunt elements. All of you understood the statement, what I said? All of you understood the statement? Yeah. So, why we are neglecting is, write in bracket here. The natural shunt elements of network, shunt elements of network or transmission line may not show a great effect on maximum power transfer capacity, may not show a great effect on the maximum power transfer capacity. Okay, done. Let's continue with this network only. ABCD parameters of this network I am going to write. Parameter A will be 1 in the sense 1 at an angle 0 degree. Parameter B is nothing but series impedance Z, which is mod Z at an angle theta. That is sufficient. After that, after taking that, simply I will write the real power equation P, and then I will say what is the condition for P maximum in this particular situation that we are going to extend. Okay, yeah, let us show. Parameter A for network what you have considered. Parameter A is 1. 1 in the sense we write 1 at an angle 0 degree. Parameter B, Z. Z in the sense mod Z at an angle theta. Simple. Mod A value 1, alpha value 0. Mod B, Z, mod Z. Beta equals to theta. Beta value is equals to theta. Fine. Parameter mod B equals to mod Z. Beta is equals to theta. Mod A value 1, alpha equals 0. Now, electrical power injected into infrared bus. Electrical power injected into infrared bus. Mod E, mod B by mod B, nothing but mod Z into cos of theta minus delta. Theta minus delta. Beta minus delta means theta minus delta minus mod A by mod B. Mod B square cos beta minus alpha means theta minus 0. Theta cos theta. That's it. Like this, we are going to need electrical power PE equation. Again, can you tell me what is the condition to get the maximum power transfer here? What is the condition to get the maximum power transfer? If you go in the similar manner of earlier, what is the condition you got? Delta equals to beta is a condition, right? Now you can write delta equals to theta is a condition. Delta equals to theta. That is a condition for the maximum power transfer. Right. Right here. Condition for maximum power transfer is delta is equals to theta. Delta equals to theta. Okay. Now you substitute the delta equals to theta condition in this, and you write the PE max equation further. Okay, please complete it quickly. So now, maximum power transfer capacity is the value of PE by keeping delta equals to theta. That is nothing but mod E mod B by mod Z by mod Z. We have cos 0 1 minus mod V square by mod Z into you have cos theta. That's it. Cos. Next thing. See, what is this theta we have taken? That is impedance angle of this network, right? Theta is the impedance angle of the network. Okay. I will try to draw impedance triangle. We'll try to draw impedance triangle. From that one, we'll take up cos theta. That will substitute in this. This is the impedance triangle of transmission line I am considering. Transmission line. Impedance triangle we are drawing here. Impedance triangle. This is resistance. This is reactance. This is mod Z, and this was the angle theta. Okay, R, X, mod Z, and this is the angle theta. What is cos theta from this one? Cos theta. R by mod Z, right? Adjacent side by hypotenuse. Cos theta equals to adjacent side by hypotenuse R by mod Z. That you substitute in that, and we will simplify the PE maximum further. Therefore, PE max equation can be rewritten as mod E mod V by mod Z minus mod V square by mod Z into R by mod Z. R by mod Z. Okay, so I'll say in the next slide. Next slide. Kindly observe. So this maximum power transfer is equals to mod E mod V by mod Z by mod Z minus what you'll get now mod V square into resistance by mod Z square. Mod V square into resistance by mod Z square. I will substitute the things mod Z value here because the mod Z is root of R square plus S square minus mod V square into R by what is mod Z square? R square plus X square. R square plus X square. Like this you can say. Yeah. Simple mathematical equations only we are saying. One small assumption I want to make now. One small assumption. I want to make this mod E value equals to mod V. Okay, like this. Mod E is equals to mod V. Like that we manipulated or adjusted the excitation. Like that we adjusted the excitation you also. Mod E value equals to mod V. Then what is the PE maximum value? PE max is nothing but mod V square by root of R square plus X square minus mod V square into resistance value by R square plus X square unit. Like this unit. Mod V square by root of R square plus X square minus mod V square into R by R square plus X square. Like this, we are going to get the expression for the maximum power transfer. Listen here. Till now, what we have done to find out the maximum power transfer. Till now, what we have done here to find out the maximum power transfer means simply we attempted to control the angular difference between the voltage sources, rotor angular difference delta, right? Based on the delta, to get the maximum power transfer, I said the condition is delta equals to theta. By keeping the delta equals to theta, we got this equation. And then we assumed that both voltages are equal, both ends source voltages are equal, and we got the PE maximum like this. From this point onwards, all of you listen here, all of you listen. From this point onwards, we are going to find out what is the condition for maximized PE maximum with respect to network elements variation. By varying these network elements, maybe resistance variation, or you say reactance variation, anything. By varying any one of these two, how to obtain maximized value of the PE maximum, that we are interested to know further. Are we getting this one? Yeah, next one. See, maximized PE maximum by varying network elements, so-called resistance and reactance means which value we have to vary. Which value we can vary easily. Is it resistance value or reactance value? I think it is better to go for reactance only. It's better to go for reactance. I will tell you the reason. Is it possible to increase the reactance value in the network? In the transmission line network, is it possible to increase the reactance? Yes. By adding series reactor. I can increase the reactance value. Next. Is it possible to decrease the overall reactance? Value? Yes. How? By adding series capacitor. We are capable to decrease the overall reactance value. But resistance, listen kindly. Resistance, we can increase it by adding series resistor. We can increase it, but we can't decrease the resistance value. Right? There is no chance of reducing the resistance value. You can only increase the value of resistance. That's the problem. That's the problem. Okay, so that's why we are considering only network reactance variation in order to maximize this PE maximum value. Okay, next one. Next, a small heading type I will take here. Maximizing PE max with respect to network reactance variation. Maximizing the PE maximum with respect to network reactance variation. How you connect the resistance in parallel? Can you tell me, Abhijit? Abhijit, how you connect the resistance in parallel? Low resistance in parallel? Connecting resistance in parallel means, is that resistance physically visible on transmission line? Is a transmission line, right? Where is resistance of a line? We can't say. Then to reduce the resistance value, you have to add one more line in parallel, right? So first line is having resistance R, second line also having resistance R, then the equivalent resistance is R by 2. Not only that, reactance also becomes half, right? Not only resistance value, reactance value also becomes half. So reducing resistance is not possible. Reducing the resistance value is not possible. Okay, yeah. Next, let's continue with this. So first of all, that PA maximum variation with respect to x, if you consider, it will be non-linear shape because denominator you have x square. So in that sense, I can say simply PA max versus x, it is of non-linear shape. And condition for maximized PA maximum, maximized PA maximum will be, yeah, look here, d by dx of PA maximum, d by dx of the PA maximum. Already you have the PA max equation, right? Mod v square by root r square plus x square minus mod v square into r by r square plus x square equal to 0. The differential term you have to find, and that you should make it equals to 0. Okay, d by dx of mod v square by root of r square plus x square minus mod v square into r by r square plus x square. This differential term we should make it equal to 0. You continue with this differentiation. If you want to do it later. Finally, the condition what we are going to obtain here is x equals to root 3 times of resistance. X equals to root 3 times of resistance. This is one of the condition for maximum power transfer capacity with respect to network elements variation. Network elements variation. Okay, you please complete this one quickly. Please complete this one. Yes, we are discussing about short transmission line. If you want, we can assume it anonymous at D. After neglecting the shunt elements, we can call the line as a short transmission line model. Short transmission line model. That does not mean that length of line is very less. The line may be having a length of 200 or 300 kilometers, but still we neglected the shunt element. We have taken only series impedance for line representation. Means it is modeled as short line. Modeled as short line. That's the meaning. Now, simply you keep this x equals to root 3r into this equation of PE maximum. Okay. So I can write PE maximum value by keeping x equals to root 3r. X equals to root 3r. Now, what you can write now? Mod v square by root of r square. R you keep as it is. Resistance value you keep as it is. Only reactance you replace with root 3r. Mod v square by square root of r square plus x square means root 3 into r whole square minus mod v square into r by r square plus x square means root 3 into r whole square. Like this. Simple. So this you can write now mod v square by square root r square plus root 3r whole square means 3r square here minus mod v square into r by r square plus 3r square means it is 4 times of r square. And you can get this like mod v square by 4r square under root 2r minus mod v square by 4r. Mod v square by 2r minus this is mod v square by 4r. And if you simplify this one, you are going to get this like mod v square by 4r. Mod v square by 4r. That is the maximized P maximum value. The condition of x equals to root 3r. The condition of x equals to root 3r. Expression for the maximized PE maximum. Maximized PE maximum. That's what I am substituting, right? Shreya, first we calculated what is the condition for maximized PE maximum. After that, you have to calculate that number, right? You write here if you want here. Value of maximized PE. Simple. In the PE max equation, substitute x equals to root 3r. This is a final maximized power we are going to get. Next. Next, I want to list out all the conditions what you have discussed. Before moving to that, see, if you are attempting to transfer this much amount of power in the transmission line network, so-called mod v square by 4r, this much amount of power, if you want to transmit, definitely power loss in the network will come very, very high. Power losses in the network will come very, very high. As well as we can say, efficiency of the system will be very, very less. Sometimes in many textbooks, the people used to give, if you operate the system with this PE maximum, efficiency may come like 50% or lower than 50% also sometimes. That statement you write first. Right? So if this much power transmitted, power was transmitted, the efficiency of the system will be very low. Efficiency of system will be very low. Efficiency of the system will be very, very low. That's why we don't encourage. We don't encourage it. Yeah. Next. Next, in the next slide, what I'm going to say is conditions. Conditions to have P max value as mod v square by 4r. What are the conditions to be maintained to get the PE maximum value as mod v square by 4r? See, majorly in the whole discussion here, you have to calculate power loss based on this current flow, right? Gopiraju, you take one network with a generator, line, and infinite bus. Okay, you take impedances as we said, and you maintain the angle as the theta what we have taken. Okay, then you find out current flow in the network. Current square into resistance is a power loss. Okay, and then you calculate the output power, which is nothing but v square by 4r. Then you are capable to get the input power, right? Output power plus power loss equals to input power. Then you find out efficiency and you confirm that the efficiency is very low, like about 50%. Okay, you confirm it and do the mathematical calculation and send to me. Gopi Raju, are you understanding what I am saying? Just take one network. Take for network, generator, resistance, reactance. Some numbers you take. And R and X values you take according to the requirement what you have chosen. Take the voltage as 1 per unit. Find out current flow. Okay. After getting the current flow, current square into resistance is a power loss. Already you know output power. Output power plus power loss is a input power. Output power by input power that you calculate. So we can say maximum power transfer does not depend on reactance of line. No. That you should not say Mudri resistor, that you should not say. Maximum power transfer value depends upon the impedance of network. Impedance of network, but you replace it that reactance value intentionally with resistance. That does not mean that it is depending only resistance here. Right? Yeah. Next. Listen here. See, two conditions majorly we have taken, right? Two conditions we have taken majorly. First condition, delta equals to theta, one condition. Second condition, x equals to root 3r. These two conditions only we are going to concentrate. Tell me, any of you, tell me, which condition I have to maintain first? Is it delta equals to theta or x equals to root 3r? Which one we have to maintain first? Anybody? Anybody please tell me. Which condition we have to maintain first? Is it number 1 or number 2? Which one? Number 1 or number 2? Look here. Okay. Listen. For example, we have taken one transmission line like this, or network, something like this. We have some already given R value and X value, right? Already given in the data some R value and X value. Based on this, we calculated the value of theta. Then I maintain delta equals to theta. That's well and good. After that, we are varying X value. We are varying X value to a number root 3r. If you do that X variation as root 3r, definitely theta will vary, right? Following the left. And your first condition already you maintain delta equals to volt theta angle. But now again you have to modify the delta value equals to theta nu. Again you have to modify the delta to be equals to theta nu. All of you getting my point? What I'm saying you? All of you getting my point? Please tell me. Right? So what condition we have to maintain first? What condition we have to maintain first? First we should maintain x equals to root 3r. Then you have to go for delta equals to theta condition in a sequence. Okay? Yeah. It's simple. I said which statement to be maintained first and which statement to be maintained later. I'll say first condition to be maintained here is x equals to root 3r. By making that x equals to root 3r, what is x-y ratio of line? Root 3. And what is impedance angle of transmission line? Means network or transmission line network. What's the impedance angle of network? Tan inverse of x by r means tan inverse of root 3 means that is 60 degree. That is 60 degree. After keeping this theta equals to 60 degree as a second one, you simply go for delta equals to theta that is equals to 60 degree. Then definitely we are going to get the maximized PE maximum, so-called mod v square by 4r. Mod v square by 4. Okay. And other conditions are there. Just I will write those other conditions also, what we said earlier. Other conditions that we need to consider other than these two major other conditions. Terminal voltages must be equal. Means source voltages must be equal on both sides of network. Force voltages must be equal on both sides of network. This is one condition we have to maintain. And one more condition we have like shunt elements are neglected. Shunt elements are neglected. Shunt elements are neglected. That's it. Fine. So now we will take up some simple problems on this concept of network elements variation. We'll take. Moving with next slide. So you go through this question. Read this question once. Look carefully what the data we have given. So here we are arranging delta to reach theta. Yes, Sai Charan. Strictly speaking, Sai Charan, we can't arrange delta, but we have to control the power flow. That's the thing, right? At what the angle we are going to get the maximum power transfer is delta equals to theta, that is equal 60 degrees. That we have to answer. Okay. Yeah. Let's move. Look at this. An alternator. We have an alternator has E equals to 1.0 per unit, XT equals to 1 per unit, connected to infinite bus, mod V equals to 1. 2. A series impedance of Z equals to 0.2 plus J 0.3 per unit. What is the nature of reactive element to be added in series with the line, and how much is the per unit reactance of it to maintain maximum power transfer in the network? Okay. Sunil, you please kindly check your settings. Is it video visible to you? Video visible to all? Kindly respond. Video visible to all? Yes. No problem here, Sunil. Just check your settings once. Yeah. Look here. Just let me keep these things what I said in a diagram. This is alternator, and we have some internal reactors for the alternator connected to infinite bus. This is the infinite bus. Mod V value 1. Internal EMF is also 1. XD 1 per unit. Okay, this is the impedance we said in the connection. Z equals to 0.2 plus J 0.3. Better, I'll write that this as J1. Okay, this is J1, and you call it is ZL network. Now, what is the overall impedance connecting between the two voltage sources here? What is the overall impedance connecting the two voltage sources here? Tell me, please. Have I given these questions to you in the student platform? Have I given these questions to you in the student platform? Yeah, good. I think all of you have downloaded. In the extra questions, it is question number 5. Okay, fine. Just go through it. Go through the question, and if you have PDF file, stability, just roll the pages and just check which question I am discussing. I said you have a print copy of that with you while I'm discussing this one. That is better. That's better. Okay. Look here. We have to consider the overall impedance of network here, not only line. We have to consider the overall impedance of the network between two voltage sources. How much is that? 0.2 plus J 1.3 per unit. Okay. Now, what is the resistance of network we have? 0.2 per unit. What is reactance of network here? 1.2 per unit. Terminal voltage here, mod E, mod V. Okay. See, in the question, it didn't say clearly. He didn't mention clearly what condition we have to use to get the maximum power transfer, right? He didn't set that condition. Even though he didn't set that type of condition, anywhere in the exam, if he is asking what is a network reactance or network element variation, we have to follow the condition as X equals to √3 R only. Okay, first you take up that X by R ratio of this network existing first. X by R ratio of network is 1 by 3 by 0.2, means it is 6.5, which is not equals to √3, which is not equals to root 3. In fact, this is greater than root 3. That is greater than root 3. All of you getting my statement? That is greater than root 3. But to get maximum power, x by r value must be equals to root 3. Or else you say x value should be equals to root 3 times of r. X value must be equals to root 3 times of r. So what you should do now? Whether you need to reduce the reactance value or increase the reactance value of network. Anybody? Tell me please. Whether you need to reduce the reactance of the network or increase. Reduce you have to do. Because old x by r ratio was greater than root 3. We have to make it root 3 in the sense, definitely we have to reduce the equivalent reactance. For that purpose, we have to add the capacitor. Okay, right. Or else, I will say this type of statement also. Resistance is remains same, na? Resistance will be remain same. X volt I will show here. Just follow the notation. X volt I am showing. Look here. X new. Done. X new. Okay. What is that X new? Root 3 into R. Resistance is remains same. That is 0.2. Na? How much is that value? Root 3 into 0.2. Anybody please tell me. What is root 3 into 0.2? Many of you are saying answer also already. Tell me please. 0.346 per unit. Okay. So as x new required less than x old. X old is 1.3. It is required to add series capacitor to reduce the overall reactance. Reduce overall reactance. Reduce overall reactance. Okay, fine. Now, in the next step, simple, very simple. I'm showing a network like this. It is a overall resistance, overall reactance of old one, and we added one capacitor. This is that infinite bus body, and this is body, and this is 0.2 plus J 1.3 minus JXC. After adding series capacitor, this is an extra element we have added in the line. Okay, now you can write from this X new is equals to 1.3 minus X, as the new reactance value required is 0.346. 0.346. Xc value will come to be 1.3 minus 0.346, and this will come to be 0.9535. 9535 per unit. If anybody is still writing in the previous slide, please complete it. I think I have followed simple rule here. Simple rule. I know already old reactance. Value 1.3 per unit. New reactance required is 0.346. So we have to reduce the reactance value. So we added the series capacitor. And after adding series capacitor, this is my network. From network, X new is 1.3 minus Xc. 1.3 minus Xc. And X new value 0.346. Make these two equal. Then we'll get Xc value like 0.9535 per unit. 0.9535 per unit. I am showing 50F, Shreya. 50F. You want to write here, it's a old network here. Old network. And this is our new network after adding series capacitor. Yeah, next. Let's take one more simple problem in the similar concept. Taking up one more similar problem in this concept. Go through this one. It's also from the PDF file, which I have uploaded extra questions. Tell me the answers for this one quickly. Everybody saying answer for this? Yeah. Look here. See, according to the data given, an AC transmission line has series resistance of 20 ohms. What shall be the impedance to maintain the maximum power transfer through the line? Actually, to get the maximum power transfer, condition will be x equals to root 3 times of R. Okay, now how much should be the impedance of line to get the maximum power transfer? Generally, impedance means R plus jx, you write R plus jx. In place of x, you keep root 3R. Then that is the impedance value to have the maximum power transfer. Okay, right. I'll say generally impedance of line is series impedance of line is it is equals to R plus jx. And for maximum power transfer condition, or simply maximum power transfer, Z will come to be R plus jx. X we will replace with root 3 into, and you take magnitude of this root R square plus root 3R whole square, and angle will come to be tan inverse of root 3R by R. Okay, so this you can get as R square, 3R square, 4R square, under root means 2R. 2R at an angle 60 degrees. 2R at an angle 60 degrees. How much is the resistance value they have given in the problem? How much is the resistance value they have given in the problem? 20 ohms. Means it will be 2 into 20, means 40 at an angle of 60 degrees in terms of ohms we have to take. Right? So what's your answer now? Answer is C. Correct answer from the options given will be C. Correct option will be C. Shushma, have you understood this? Shushma. So next, we are taking up on simple discussion here further. So I'm moving to the next slide. I'm taking up SMIV. Taking up on simple SMIV. Single machine connected to infinite bus bar. Yeah, Srikant. I'm explaining this, kindly observe here. Srikant. Resistance of line is given 20 ohms. Generally, impedance of line is R plus jx. That's it. Impedance of line is R plus jx. But in order to maintain the maximum power transfer, this x value we should maintain as root 3 into R. Then what will be the value of impedance to maintain maximum power transfer? That is R plus j root 3R. I have taken magnitude of that and associating angle. Already resistance is given in the problem. And I substitute. That's it. Simple. Okay. So now I am considering again single machine connected to infinite bus bar here. Single machine connected to infinite bus bar. We explain you some more thing. I am taking up this SMI. Look. So this is the alternator. You consider if you want only reactance. Resistance I am neglecting. The resistance I am neglecting. Only reactance. All reactance is taken as a single element, and this is infinite bus. Like this. And this is something like mod E at an angle delta, and this is something like mod V at an angle 0, and this is Jx. I'm saying you again, don't ask me again, where is the generator reactance that was taken into this X. Generator reactance was taken into X. That's it. Electrical power injected PE. Electrical power injected PE. What is the expression for PE? Mod E into mod V by X into sine delta. Mod E into mod V by X into sine delta. See, for example, if you want to use ABCD equation, that also you can use, but it's a simplified one of that ABCD equation. Just all of you look here. All of you look here once. Look here. E equals to mod E into mod E by mod B cos beta minus delta minus mod A by mod B square cos beta minus alpha. That's it. What is parameter A of network? What is parameter A of network? 1. Because no shunt element here, 1. 1 at an angle 0 degree. What is parameter B of network? What is parameter B of network? Anybody? Jx. X at an angle 90 degree. All of you look here. All of you look here quickly. 1 at an angle 0, x at an angle 90. So this beta you can keep 90 degree. And this beta you can keep 90 degree. Alpha you can keep 0 degree. Cos of 90 minus 0, cos 90, 0. Cos of 90 minus 0, cos 90, that will be 0. Second term will become 0. In the first term, we have mod E, mod B. What is mod B? X. Cos of 90 minus delta, sin delta. That's it we have written, right? EV by X into sin delta. All of you understood this? I think you don't have any issue with this one. I think so. Because earlier we discussed about the ABCD equation. That is the original equation. And with the approximation of only series reactance of network, we can convert that equation into only series reactive network equation, which is coming like EV by X into sin delta. EV by X into sin delta. You keep this one aside if you want. Okay, fine. Next, let's continue this. What is this EV by X we have got? Maximum power transfer capacity of the network. Maximum power transfer capacity of network, P maximum. So it is P maximum into sin delta. Let us say PE, something like this. It is a function of delta. PE variable with respect to delta, right? So I have written this one. PE of delta is equals to P maximum sin delta here. P maximum sin delta. Next. Listen to this. At initial operating condition, the electrical parts at the rotor angle, you take rotor angle. Rotor angle is delta naught, right? At initial condition, rotor angle is delta naught. With that rotor angle delta naught, look, with that rotor angle delta naught, what is that electrical power? What is that electrical power P of delta naught now? That is nothing but P maximum sin delta naught. P of delta naught value is nothing but P maximum sin delta naught. Simple. Next. Look here. Look here, all of you. Look here. A small disturbance occurred in the system. Whatever it may be. Forget about the disturbance type and all. Simple. Small disturbance occurred on the system. It caused for a rise in the angle or for an increment in the angle by a small value delta. Okay, a small disturbance occurred in the system. It is causing a rise in the rotor angle by a value of delta. It's a very, very small angle. Okay, a small disturbance caused for increment in the angle by a small value delta. Increment in the angle by a small value delta. Then what will be the new angle you can experience now? What's a new rotor angle? What is a new rotor angle? That is nothing but delta naught plus delta. New rotor angle will be simply previous angle delta naught and that increment what we have now delta. Now at this new angle of delta naught plus delta, what is it electrical power? What is the value of electrical power at this new rotor angle? Electrical power that PE of delta naught plus delta delta, PE of delta naught plus delta delta is equals to, look here, P maximum sine of delta naught plus delta delta equal to P maximum sine of delta naught plus delta delta equal to. Simple. It's like sine A plus B expansion. Sine A plus B expansion. You please expand it. Sine A cos B plus cos A sine. Okay. You please complete it. I will move to next slide. Take up that expansion of that further. Okay. So I'm taking in the next slide. So it is P of delta naught plus delta delta is equals to P maximum sine delta naught cos delta delta 1 term plus P max cos delta naught sine delta delta, that was second term. Next. See, actually, yeah, as we are saying that delta delta is a very small angle. Delta delta angle is very small. So definitely I can assume now delta delta is very small. Very small. Cos delta delta, we are going to take it as 1. Cos delta delta, we are going to take it as 1. Sin delta delta, it will be coming like delta delta radians. We are going to write it like delta delta in terms of radians. Sin delta delta, it will be delta delta in radian. Cos delta delta is close to 1. Okay. Of course, you may feel that sin delta delta is 0. Close to 0, that's sure. But I want to keep that as in terms of delta delta radians. Okay. So therefore, you can keep this P of delta naught plus delta delta value is equals to P maximum sin delta naught cos delta delta is 1 plus P maximum cos delta naught into delta delta in terms of radians. Delta delta in terms of radians. Okay. Now, what is this one? Anybody? P maximum sin delta naught is what? This is nothing but P of delta naught, right? That is nothing but P of delta naught. That's what we have written earlier. P of delta naught is P maximum sin delta naught. Okay, you take the P of delta naught to the other side. P of delta naught to the other side. So I'll say here P of new electrical power is P of delta naught plus delta delta minus P of delta naught we have, right? P of delta naught name is old electrical power. P of delta naught name is old electrical power is equals to P maximum cos delta naught into delta delta. P maximum cos delta naught into delta delta. Does anybody tell what is this one? It's a new electrical power minus old electrical power, right? New electrical power minus old electrical power, that I know. What's the meaning of that? What's the meaning of that? Okay, good. Change in power. Change in the electrical power. Because of what? Because of what? Because of what? Disturbance. See, this term what I have highlighted here, it is the increment in the electrical power developed by generator. Increment in the electrical power developed by generator because of the disturbance created. Because of the disturbance created. This we are going to name as synchronizing power of the alternator. Okay, so this we are going to name as synchronizing power. Synchronizing power. In bracket, I am writing that simple definition. It is The change in the power developed by alternator, change in power developed by alternator for small disturbances. Small disturbances. I think all of you getting this one? For small disturbances, whatever the change in the electrical power developed we have, that we are going to call as synchronizing power. I will call this with a letter delta PE from this point. Calling that letter as delta PE. Now the disturbance is delta delta, right? In terms of radian. You take that to other side. So finally, what you can write here is delta PE by delta delta. Simple. Delta PE, and this is delta delta. What is that now? It is the value P maximum cos delta naught. Is the value P maximum cos delta naught. Right? And as this delta delta is a very, very small value, delta delta is very, very small value, we can rewrite this delta PE by delta delta as dPE by d delta also. We can write it as dPE by d delta also. Yeah. I'm showing 57. If anybody is still writing, complete that 57 slide. If anybody is still writing 57, please complete it quickly. Okay. So, as delta delta is very small, you can write delta PE by delta delta as dPE by d delta. So finally, you are getting this as dPE by d delta at an angle of delta naught. That is nothing but P maximum cos delta naught. P maximum cos delta naught. This is going to be called as synchronizing power coefficient of the network. It's going to be called as synchronizing power coefficient. Power coefficient. Else, sometimes we can call it as rigidity factor of the machine. Rigidity factor means how much rigid the system is in accepting the small disturbances. How much rigid the system is in accepting the small disturbances. That we can say rigidity factor. Yeah, this is again same what we discussed earlier. P equation we have simply P max sin delta. Right? Let's say P equation we have simply P maximum sin delta. And what is the dPE by d delta? What is the dPE by d delta? This is nothing but P maximum cos delta. Okay, this value, slope value, what we discussed earlier, slope value, if the dPE by d delta at the angle of delta naught, at the angle of delta naught where you are standing, that is called as synchronizing power coefficient. That's okay. Rigidity factor, or you can say electrical stiffness. Electrical stiffness. All these terms are same. We are saying all these things are steady state. Okay, so now I will be showing the power angle curve, PE versus delta, as well as synchronizing power coefficient curve, dPE by d delta. Based on that, just I will show you in what region the system is stable in the power angle curve, as well as in what region the system is stable in the synchronizing power curve. Okay, yeah, simple. I'll take in the next slide. Look here. Just P equation we have P maximum sin delta, dPE by d delta also P maximum cos delta. I will show that graph here, kindly observe. P is delta axis. This is delta axis, okay? And it is also delta axis I am showing. axis. I am showing power and dp by d delta axis here. This is 0 degree, 0 degree. This is 90 and 180, 90 and 180, and here also 90, and this is 180. And this side you have minus 90 degree, minus 180 degree. I'm showing in the negative portion also. Minus 180, minus 90. Simple, simple. Next. Power angle curve. I will be showing like this power angle curve. Okay. And this is a peak. What we are saying is P maximum. This is a peak we are saying is negative P max. Next, dp by d delta curve we are going to draw. dp by d delta, which is P maximum cos delta. P maximum cos delta. That curve will come between minus 90 degree to plus 90 degree positive. Between minus 90 degree to plus 90 degree, we are going to get this as positive. And then it will go negative like this. Negative like this. So this curve is dp by d delta curve. Let me show. This is E curve, and this is dp by d delta curve. And what is this value? Anybody please tell me what is this value? Anybody? What is this value? P maximum, right? That is also P maximum. And you know, angles I am showing. This is minus 90 degree angle. This is plus 90 degree angle. And this will be again minus 90 degree angle. And this will be again plus 90 degree angle. Minus 90 degree, plus 90 degree. Okay. Simple question to you. Simple question to you. When we can say system is stable? When we can say the system is stable? Very simple. When we can say system is stable? If the operating point lies in the positive slope region, then the system will be stable. Right? Tell me, in the power angle curve, what I have shown, in what range of angles? In what range of angles you have positive slope? In what range of angles you have the positive slope? In what range of angles you have the positive slope? Simple. That is starting from minus 90 degrees to a point of plus 90 degrees. Right. So in this region, we have the positive slope. Getting all of you? Starting from minus 90 degree to plus 90 degree, we are going to get this as positive slope. So in this region, if you lie anywhere, we will say that the system will be stable. Say that the system is stable. Okay, so I'll write in the other words, the next one. The system is stable. System is stable, but the angle in the zone of minus 90 degree to plus 90 degrees. Minus 90 degree plus 90 degrees. Now, in case of dp by d delta curve, so-called synchronizing power coefficient curve, if you want to show that stable region, you should show it starting from minus 90 to plus 90 only. There is no change in that. And this value will be positive. That's what I'm saying. The positive portion of dp by d delta, we can say that the system will be stable. Positive portion of this dp by d delta, we are saying that the system will be Negative portion, it is going as positive. Yeah. Next. See, generally, stability angle of system. Look here, stability angle of system means that is the angle at which we are going to touch the maximum power. We said it is 90 degree in this particular situation. In this particular situation, we said it is 90 degree. Okay. So stability angle of system in this case, stability angle of the system in this case will be 90 degrees. In case of the network having some resistance and all, look here. In case of resistance is there, shunt elements and all, right? If that is the case, obviously you are going to get this angle delta equals to beta. Delta equals to beta as a stability angle, right? And what are the preferable operating angles in the system? What are the preferable operating angles in the system? Means generally we prefer to operate the system in the range of 30 to 45 degrees. 30 to 45 degrees. Why it is so means, in order to maintain good stability for the system, not only for steady state disturbances, as well as for transient disturbance also. To maintain good stability for the system in the steady state as well as the transient, as well as to have an appreciable amount of power flow. To have an appreciable amount of power flow, it is required to consider that angle delta in the range of 30 to 45 degrees. That we are going to name as preferable operating angles of system. Operating angles of system. Delta, it will be 30 degrees to 45 degrees, right? So in the view of system stability, and good power flow, good amount of power flow, as well as good amount of power flow. Actually, delta value can't be negative 1 in synchronous generator. Then how can we draw minus 180 to 0 degree? Yeah, Shiva, you don't think this only in the view of a synchronous generator. This you think simply in the way of whole power system network. Simply you think this in the way of whole power system network. In the way of whole power system network, definitely we may get the negative angle also. At some buses. So at that negative angle, to say whether the system is stable or unstable, you should check the slope again. So this is not confined to only generator. I am saying this is in general way. Okay. I am asking you again. Please tell me. Have I uploaded the PDF file in the portal? Have I uploaded the PDF file in the portal? Please tell me once. Yes. If all are looking at that PDF file, how come you don't have that PDF file, Mr. Anonymous Attendee? How you are posting the same question again and again in portal? No PDF is uploaded, sir. I checked. As if all people are getting the PDF file, how come you are not getting it? All people are saying that there is a PDF file in the portal. How come you don't have it? Yeah. See, all generators used are synchronous machines. That's okay. Look here. All machines are synchronous machines only. But if you are going with other buses, maybe if you take, let's say one of the generator you are taking as reference, right? Other bus voltage angle might be negative, right? That may be a chance. That's why I'm saying in a concluded way, in what range of angles the system will be stable. Yeah, fine. Next thing. I will take up some simple questions on this whole steady state stability analysis, what we have discussed now. Later on, we will see what are the methods to improve the steady state stability of the system. Okay, yeah. So let's see. First question. Again, from that additional questions only, PSA additional questions. I'm taking up some simple questions. Wait. Make it quick, please. Please kindly don't join as anonymous attendee. Kindly. Some people are there, some good people are there even in the anonymous attendee category. I'm requesting you, don't join as anonymous attendee category. I don't answer for your questions. Okay? Yeah. Next. Look here. An alternator. If you have any problem of joining with your name, let me know. I will tell you the solution how to join with your name. Don't join as an anonymous attendee. It's my kind request. Whichever the question you post as an anonymous attendee in the Q&A, I may not be answering those questions. Look here. An alternator rated for 11 kV, 500 MVA has the series impedance value J1. Series impedance of alternator is said as J1 ohm. No resistance is given. Only reactance value 1 ohms. Okay. The internal EMF and terminal voltages of the alternator are 13 kV and 11 kV respectively. The value of maximum power transfer in per unit by taking machine ratings as base values will be dash per unit. Kindly observe it. Kindly observe it. Okay. See, this is one alternator existing. Ratings of this alternator will be ratings 11 kV, 500 MVA. 11 kV, 500 MVA. I'll say it's a line-to-line voltage, and this will be the three-phase apparent power rating. And the reactance of this machine directly, I'm saying it is 1 ohms. Internal EMF E mod E. Of course, it is line-to-line value. Mod E in the sense it is line-to-line value. This is 13 kV. And how much is terminal voltage of alternator? Mod V 11 kV line-to-line value. 11 kV line-to-line value. Okay, next thing. Listen. What is maximum power transfer capacity of this network? By choosing the base values as machine ratings. Generally, if you have simply reactance, maximum power transfer will be, just look at this formula for maximum power transfer. That is mod E into mod V by X. X means generator reactance we have to consider. Okay, I didn't told this statement to you. Kindly observe. What is this P maximum value? Is it three phase or per phase? Is it three phase or per phase? We didn't discuss about it till now. For example, if you feel this is per phase value, then it will be E phase, B phase we have to consider. What do you mean by three phase P maximum? What do you mean by three phase P maximum? 3 into E phase magnitude into V phase magnitude by X. Okay, that is nothing but root 3 times of E phase. Again, root 3 times of V phase you can write by X value. X value will be remains per phase only, right? X value will be remains per phase value. Okay. See, what is it? Root 3 into E phase you can write? E line to line magnitude. E line to line magnitude. And what is it? Root 3 into V phase? That is V line to line magnitude by reactance value in terms of ohms. Okay, simple. You keep the values of EVX, what you have in the original form, means in the absolute form you substitute. What is E line to line? 13 kV. What is V line to line? 11 kV. So this is 13 kV and this is 11 kV. By X value was 1 mole. And kilo square, and it will be megawatts. This is the maximum power transfer capacity. How much is this one? How much is this one? Tell me please. It's not that reason, Bhruv and Satish. It's not the reason of 30 to 45 degrees. Okay? The reason is to have good power flow along with good stability. To maintain that one, we are taking it. It's not sine cosine values as equal. 143 megawatts is a value of P maximum, three-phase number. 143 megawatts. And how much is the per unit value of this? Means this we have to divide with the S base. What is S base? S base is 500. So I can say P maximum value in per unit form is 143 by 500. Absolute value, you write formula as we are doing this for the first time now. Write the P maximum absolute value megawatt by S base in terms of MVA. So it is 143 by 500. 500. How much is this number? Anybody? Please tell me this number. X is given in the data, right? Ashish Raj, X value they have given in data 1 ohm. 1 ohm. It will be 0.286 per unit. This number will be 0.286 per unit. So in the blank, we have to give the answer as 0.286. Okay? Yeah. Next. Let's take one more simple question based on this maximum power transfer calculation. So the previous question just now what we have discussed, they have asked in ESC prelims, means in the objective examination they have asked this question. ESC prelims. Okay. Now you see this question. This is one of the expected question in the GATE examination. One of the expected question in the GATE examination. Go through this one. Now the model, we can say till now this type of question we don't have in any exam. In any exam we don't have this type of question. This is having a chance. This is having a chance of getting in the exam. Go through this. Find steady state stability limit of the following system in which alternator EMF is 16 kV. Alternator induced EMF is internal EMF is 16 kV. Of course it is line to line. Of course it is line to line. Okay. And infinite bus voltage is 400 kV. That is also line. What is the value of P maximum of this? Did he mention anything regarding base values in the problem? Did he mention anything regarding base values in the problem? No, he didn't mention any base values here. So in what units we should give our answer? Absolute form. Means in terms of megawatt, you have to give your answer. Okay? Tell me, let's continue with this. This is a single line diagram given for you in the data. If you want, you draw it quickly in your notes. Next slide. Listen all of you. Good. In question, will they mention whether in per unit or megawatt? They don't mention it. Actually, Vishnu, if they have not mentioned anything, whether it is in per unit or megawatt, you attempt to give that in absolute form. For example, if all the values in the question are given in per unit form only, they will ask you to give the number in per unit only. Yes or no? If they have not mentioned anything, whether to give the answer in per unit or absolute, we have to give the answer in the absolute form in a preferable way. Yeah, let's move. Can you observe? Yeah, so I'm showing the question slide. I will explain here itself because same diagram I have copied there. Listen. As you have transformer, it is preferable to go the analysis in the per unit domain first. We'll attempt to do this problem in the per unit domain first. After that, we convert this into absolute. All of you getting this one? Now, if you want to do these calculations in per unit form, first we should choose some common ways. Let us assume generator ratings itself as base values. 11 kV, 500 MVA. These values itself we are going to assume as base values. Okay, let's write here. Let 11 kV line to line voltage, 500 MVA, three phase apparent power. These are base values of generator. Base values at the generator location. Let me write these base values here. I'm choosing 11 kV, 500 MVA. Yeah, again, I'm saying it's your wish what to choose. Because ultimately you have to give answer in absolute, right? See, actually, these base values are varied up to this transformer location. Beyond the transformer winding, means from the secondary winding of transformer, what will happen to base values? New base values on this side, 500 MVA as it is, it will be continued, no change. Okay, what is voltage base? Voltage base will be 11 into 400 by 11. That's the transformation ratio of transformer, right? So it will be 400 kV. 400 kV, 500 MVA, those are the base values to be continued further. Yeah, if asked in per unit, then assume basis. Actually, Sai Charan Reddy, and all of you listening here, if they are asking answer in the per unit domain, they will give the base values in the problem. Because if you choose a base values arbitrarily any numbers, your per unit values will be definitely different answers. Will give different answers. Following all of you, right? Right. Let's continue. With this. Now, is it required to change this generator reactance? No, because old base 11 kV 500 MVA, new base is also 11 kV 500 MVA. What about transformer? Anybody tell me please? Transformer. Is it required to modify transformer reactance? No. You take on primary side if you want. Primary side. What's the old base on primary? 11 kV 500 MVA. What's the new base on primary? 11 kV 500 MVA. So you no need to modify the transformer reactance also in terms of per unit form. But line reactances they have given in terms of ohms. So we have to convert this line reactance into per unit form. Line reactance we have to convert into per unit form. Not only that, internal voltage of alternator, infinite bus voltage, these values also we should convert into per unit form. So first we do for line. For lines, XL value 100 ohms. Is it? Yeah, 100 ohms. And base values already you know here. Base values are 400 kV line to line. And then you have 500 MVA 3 phase. And what is Z base value from this? Z base value. V base line to line square by MVA base 3 phase. Kilo square mega will be cancelled out. So it is 400 into 400 by 500. 400 into 400 by 500. Anybody please tell me this number? This is 320 ohms. 320 ohms. Then how much is the value of XL in per unit form? XL actual value 100 by base value was 320. XL actual value 100, base value was 320. How much is that number? 0.3125. 0.3125 per unit. Okay, just look here. Somebody is having a doubt regarding transformer. They have given the transformer reactance in per unit form already 0.2 by choosing these ratings as base values. Okay, after checking the new base values, it is observed that new base values what we have and the old base values both are exactly equal. So that XT per unit will be remains as it is. Okay. Now we will draw the per phase model. Per phase network you can say. First generator, voltage source in series with some reactance for generator like this. And then we have a transformer represented in this manner, transformer. After transformer, you say two lines are there. Line 1, line 2. connected in parallel. And at the end, you have infinite bus. Infinite bus means it is represented again as a voltage source. Again as voltage source. Yeah, next one. Look. What is this internal EMF mod E in per unit form? What is this voltage mod V in per unit form? You know already, generator reactance is 1.0 per unit. Okay. Transformer is 0.2 per unit. First line 0.3125. Second line 0.3125. What is it mod E value actual? Oh, why does we take VS as internal EMF rather than taking bus voltage of generator? They have given internal voltage, right? In the problem, they have given 16 kV as internal EMF, right? Yeah, I've shown the previous slide. Tell me please, mod E value given in the data, that is 16 kV. 16 kV. And what is the base here? What is the base here? 11 kV. Then what is the value of mod E per unit? 16 by 11. 16 by 11, we should say. What is the infinite bus voltage mod V? 400 kV. What is the base value here? 400 kV. 400 by 400, 1 per unit. So, internal EMF in per unit form, actual value 16, base value 11. Calculate it and tell me. Infinite bus voltage, actual value 400, base value also 400. Anybody tell me please, what is that internal EMF? 1.4545. Good. 4545 per unit. 1.4545 per unit. Now, you simply convert this whole network into a single element model, and then you find out the maximum power transfer capacity. So I can say X equivalent value now, this combination, 1 plus 0.2 plus 0.3125 in parallel to 0.3125. Okay, so equivalent transfer reactance of network. 1 plus 0.2 plus 0.3125 by 2. How much is this number? Anybody, this reactance value? 1.35625. 1.35625 per unit. Therefore, maximum power transfer capacity of this network in per unit form you are going to get first. It is mod E, mod V by equivalent reactance. What is mod V value? 1.4545. 1.4545. Mod V 1. X value 1.35625. Anybody tell me this number? Tell me that maximum power transfer value 1.07. Somebody is saying 1.069. Okay, 1.07. Calculate properly that number. In the narrow range, you may miss the options sometimes. 1.7244. Good. 1.7244 per unit. But you need to give this number in absolute form, right? Of course, he is asking steady state stability analysis, steady state stability limit in the problem. Steady state stability limit in the problem. That is nothing but Pmax only, right? Steady state stability limit value or P maximum, both will be same. And you have to give this number in absolute, means in megawatt. With what base you have to multiply this? What base you have to multiply this one? 500 MVA base. You have to multiply this with 500 MVA base. So P maximum in terms of megawatt is nothing but three phase value only we are asking. P maximum per unit number into S base. To take it as 3. So it is 1.07244 into S base is 500. Resultant units will be in megawatt. So that value will be 536.22. 536.22 megawatts. 536.22 megawatts. Yeah, so I'm explaining again. But is asking very simple. In the question, they have given this diagram, asked us to calculate the maximum power transfer capacity value. as a network is consisting only reactances here, network is consisting only reactances, maximum power transfer formula mod E into mod V by X equivalent. But the network is having some transformer here, so I can't do this problem in the absolute domain. It is better to go with per unit domain first, then you convert it back to absolute form. Okay, so to do this in the per unit domain, we have to select our own base values. That's why I have chosen generator ratings itself as base values. I found the base values at the other location. And I converted all the reactances in the network into per unit form. We have drawn the per unit per phase mode. Okay, and absolute value of induced EMF given as 16 kV, that has to be converted to per unit by dividing with 11. Infinite bus voltage is given 400 kV, convert into per unit form by dividing with 400. After getting it, we calculated the value of X equivalent, and finally P maximum value per unit form. And we have to, if you want to convert this into absolute form, we should multiply that with the S base. And finally, we get this one as 536.2. Clear? Yeah, fine. Next, we'll take up one more simple problem. One more simple problem. Go with this. See this one? One more definition I want to tell by using this problem to you. One more definition I want to tell you. Just look at this. An alternator connected to infinite bus through a transfer reactance of 0.3 per unit. Okay, fine. The internal EMFs of alternator and infinite bus are mod E 1.2 per unit, mod V 1 per unit. The system is operating with a stability margin of 40%. The synchronizing power coefficient or electrical stiffness or rigidity factor of the system is dash per unit megawatt by electrical radian. Per unit megawatt by electrical radians. See, listen. Listen here. Listen here. See, actually, we discussed about synchronizing power coefficient just now. Let me go into that slide once. Synchronizing power coefficient slide. This one. What will be the units of synchronizing power coefficient? Anybody tell me, please? What will be the units of this one? It is P by delta, right? Differentiation of power with respect to delta means it will be megawatt by electrical radians. You have to write it as megawatt by electrical radian. That is the units of this dPe by d delta. Fine. Next, let's move to the problem. Of course, in the problem also they said the same units, but we are dealing with per unit power. That's why they have written it as per unit megawatt by electrical radian. Per unit megawatt by electrical radians. Okay, next thing. Listen. This is alternator connected to infinite bus bar through a transfer reactance of 0.3 per unit. If you want to write in the form of impedance J0.3, but in the maximum power transfer equation, you should take only X value. Okay. Next, internal voltage of alternator is 1.2. Infinite bus voltage is 1. System is operating with a stability margin of 40%. This is one new term what we got here. Okay. So stability margin is equals to 40%. I will explain about that stability margin. First. Later on, we will do the remaining points what they have given in the question. Yeah. Look here. So I'm showing the power angle curve. Power angle curve. P versus delta. This is a power angle curve. And this is a maximum power transfer capacity, P maximum. Just listen here. Very simple thing. At present means at the present operating condition, the power flow in the network is P naught. So this is the present power flow in the network with an angle of delta naught. Delta naught. Please kindly observe my words, what I am saying you. Listen. See, if the maximum power transfer capacity of network is 2 per unit, maximum power transfer capacity of network is 2 per unit. Is it the meaning to say 2 per unit is flowing in the network? I need your answer. All of you have to give the answer. If the maximum power transfer capacity of network is 2 per unit, is it the meaning to say 2 per unit is flowing in the line, means flowing in the network? No, 2 per unit is simply, you are saying steady state stability limit. You are saying that is simply steady state stability limit. Now, power flow in the network might be lower than 2 per unit. That depends upon your initial operating condition. Following all of you? Fine. See, this is the present power flow in the line, that is P naught. You see, whatever the gap you have between present power flow and limit P maximum and the P maximum limit, this gap is going to be known as stability margin. Gap will be called as stability margin. I think all of you getting my word, what I said. Stability margin is nothing but the gap between present power flow to maximum power transfer limit. So if you want to give that stability margin in megawatt, that is the value maximum power transfer capacity minus present power flow. But if you want to give this in percentage form, divide that with P max. Percentage stability margin, if you want to give, you take it as P maximum minus P naught by P maximum into 100%. Clear? Now, else as a simple layman language, if you talk, 30% stability margin. 40% stability margin means this value was 40%. What is the remaining value here? 60%. Means how much is power flow in the network? We can say 60% of P maximum is a power flow in the network. Like that you have to call. 40% stability margin means the present power flow will be 60% of the maximum power transfer capacity. Yeah. So I'll say in the next slide. 40% stability margin. Stability margin implies present power flow. Present power flow means P naught is nothing but 60% of P maximum. 60% of P maximum. So it is 0.6 times of P maximum. 0.6 times of P maximum. And what is asking now? Just look back to the question now. What is asking exactly? What is the synchronizing power coefficient of the network? What do you mean by synchronizing power coefficient? dPe by d delta. Already you know power equation P equals to P max into sine delta. Okay, and the value of synchronizing power coefficient dPe by d delta, dP by d delta, we have taken dP by d delta. This is P maximum cos delta. Simply, we have to keep delta naught. In this one to find out the synchronizing power coefficient at the present operating condition. So dPe by d delta at an angle of delta naught is nothing but P maximum cos delta. Okay, and P maximum value, how we can get? Just look into the network, can get it P maximum simply. mod E into mod V by X. That will give P maximum. From network, you can say P max is mod E mod V by X. Mod E value 1, V value 1, X value 0.3. This number will become 4. P maximum value was 4. What is delta naught now? What is delta naught? To get the delta naught, they set the value of P naught, 0.6 times of P max. Okay, so from equation, initial power flow P naught is P maximum sine delta naught. P maximum sine delta. And already I know P naught equals to 0.6 times of P maximum from data. From these two, I can call sine delta naught value 0.6. Sine delta value 0.6. Okay, you calculate cos delta naught from this one. You calculate the value of cos delta naught from this one, you will get 0.8. Cos delta naught value, you are going to get like 0.8. You calculate it. First, you calculate delta naught, apply cosine, you may get that number as 0.8. Now, the synchronizing power coefficient value at an angle of delta naught, nothing but P maximum cos delta naught, P max number 4, cos delta naught number 0.8. Units will be megawatt by radian. Megawatt by radian. This is per unit megawatt by electrical radian, we have to call. Per unit megawatt by electrical radian. How much is this number? It will be 3.2. 3.2 in the respective units. So we should give our answer in the blank as 3.2. Give our answer in the blank as 3.2. Okay. So we have a break for 10 minutes or 15 minutes. 15 minutes break, I am saying. So after that break, we'll be continuing with some more problems here, and then we will think methods to improve the steady state stability of the system. How to convert this value into absolute form? We don't know the base values, right? We don't know the base values. So actually, if there is a per unit, there should not be megawatt. It's not necessary. Anonymous attendee. It's not necessary to say. It's not necessary. Per unit or per unit megawatt. That's okay. That's okay. Yeah. Fine. Have a break for 15 minutes. After that, we see some more problems.